This is my favorite chapter because it's oh so interesting, and because even though I am a recent citizen here to Oak Ridge, I've only been living here 10 years, I really love this city. I think that it has a spectacular history. I think if you were to get a bunch of historians together, many of them would probably list Oak Ridge as one of the top 20 most influential cities in human history. I mean, before you pshaw that, consider Manhattan Project. Not only that, but the incredible amount of technology that was developed right here in Oak Ridge after the Manhattan Project. This is perhaps one of the most influential cities in human history. At one time, this had the largest building ever created in human history. A mile-long building called K25. So, when you associate Oak Ridge, you think of nuclear chemistry. So let's study a little bit about nuclear chemistry in order to understand the basics that we will need in order to watch a really cool video called The Secret City, in which you'll go back and wonder, geez, why was I living back then when Oak Ridge was a fun place to live in? Yeah, not the way it is now. Okay, so let's review. Chemical reactions take place where? What part of the atom? Not just the electron shell. What part of the electron shell? The outer shell. So most of what we do in chemistry involves the potential for 8 electrons. That's it. The outermost shell of an atom. Nuclear reactions take place in the nucleus. Nucleus. Yes, Alex. So, let's talk about the nucleus. What are some of the properties of the nucleus? Well, it's very small. If a nucleus was a ping pong ball, the first electron that you would encounter would be about 1/3 of a mile away. Whoa. It is also very dense. So if you had a ping pong ball that represented your nucleus, that ping pong ball would weigh 2.5 billion tons. So as you can imagine, an atom is made up of a really dense middle with mostly just empty space. Don't call it air. It's not air because this is much smaller than air. It is just empty space. The reason why nuclear chemistry is so important to us is because we're talking about energy. It's to the order of 1,000,000 times greater than any kind of chemical reaction. That is why our future is in nuclear chemistry. Folks, I don't know where you fall in the whole global warming debate, whether you think that the warming trend that we experienced in the 90s and the 21st century is part of a trend that's going to keep going up because of humans, or whether you believe that it is part of a natural cycle. It doesn't matter. We're running out of petroleum. We're using up all our petroleum, not all, but a lot of our petroleum for energy. We need to get off of that. Because for no other reason, I want to keep my plastic doodads. I mean, think about it. You're writing with plastics. That's oil. You're writing on plastics. That's oil. You're wearing plastics. That's oil. You're eating plastics. That's oil. Any type of plastic that you use, the capsules have a plastic coating on it. When you take medicine, okay? Yes?
The last thing you said was energy involved is about 1,000,000 times greater than a chemical reaction. Is that why when people talk about splitting an atom, it creates a huge explosion?
Yeah, I mean, we'll consider that you drive down Edgemore Road and you encounter Bull Run Steam Plant. And you have a valley full of coal. That's enough coal for maybe a week for the Bull Run to run on. Okay? Now, compare that to a nuclear reactor, which would use roughly a large suitcase worth of fissionable material for the whole year. That tells you right there that the nucleus is able to release far more energy than any kind of chemical reaction. Okay? Fission is what we do now. We split atoms. Our future is in fusing them together. Fusion. Okay? Until we get to fusion, human history is right now at a very precarious point. Yes?
Have you heard about the international project in France?
CERN? Yeah.
ITER project.
The ITER project, yes. Yeah. Yeah, I mean, it's out there. Our hope is that sometime in your lifetime we can do nuclear fusion, and then humans can continue. Yes, Alec?
So why don't we invest in nuclear energy now?
Very good question. Very good question. A lot of it is politics. Nucleons. What are nucleons? Protons and neutrons. After today, you should be able to explain what ionizing radiation does to living tissue, and you should be able to compare and contrast between alpha, beta, gamma radiation in terms of composition, symbols, and ability to penetrate. Behold Marie. You see Marie? Marie is a very good example of a relatively unstable person. Okay? So Marie has been Marie. Now, as always, you're going to wonder, where the heck is he going with this? And then I'm going to bring it back to chemistry, and you're going to go, ah. Okay, but for now, just enjoy the road. Enjoy the ride. Marie. So Marie has been Marie for the past 15, 16, 15, 16? 16 years. Okay, and are you dating anyone?
Yeah.
What's his name?
Cody.
Cody. Oh. So imagine Marie and Cody walking down the hallway, hand in hand, so sweetly, so romantically, and then Marie stops and gets a really weird look on her face. And she starts going, oh, no. Cody looks at her and goes, Marie? And Marie's going, and then all of a sudden there's a blinding light. Cody is hit with a piece of sticky stuff. He looks down after his eyes start working again, and there's like a bloody piece of flesh, which he promptly throws on the ground and wipes his fingers, trying to wipe off the blood off of his fingers. And then he looks at Marie, and there's a dude standing there wearing Marie's clothes. Not very well. He has his own hair. So, Cody goes, Marie? And the dude looks at him and goes, Matt. Marie? And the dude goes, Matt. So at this point, Natalie's come upon the scene, and she realizes what has happened, and she starts taking Matt over to guidance, where in this world, guidance has its own little special counseling center where it helps people who have undergone the change. So Marie is now Matt, and Matt has to have some men's clothes because he's a guy, and right now he was squeezing into those pants that are like 2 different materials that she has on. Okay, and so Matt is the people in guidance have to put Matt's information now because it's not Marie Gubank anymore. It's Matt Gubank.
Where'd Marie go?
Marie's gone.
Oh, I know what happened.
Hush. So Matt comes out, and there's Cody, and Cody looks at him and goes, "We're breaking up." And Matt goes, "Good." It was going to get awkward. So Matt goes on and comes to class here. Natalie all of a sudden starts messing with her hair. I noticed that she's curling her hair, and she's everything that Matt says, Natalie giggles at. I'm going, what is wrong with Natalie? She's giggling all the time now. And I realize, oh, Natalie likes Matt Gubank. Okay? So, Weeks and weeks pass by, then pretty soon you see Natalie and Matt coming in hand in hand. Oh, yeah. Matt and Natalie are now dating. Okay, we come upon April, May, and then May, on a beautiful spring day, Matt and Natalie are walking down the street. And Matt stops, starts looking like this, starts groaning. Oh. And Natalie's going, oh no, no, Matt, no, no, Matt, no. Yes. Flash of light, piece of flesh. Natalie wipes it off on her pants. She looks, and there's a girl staring back at her. Matt, is Natalie's response, and the girl looks at her and goes, Susan. Matt? Susan. These clothes are really big. So Natalie takes Susan back home where she helps her with some new clothes, and Natalie goes, Susan, I'm not comfortable with this. Susan going, well, your loss. And so Susan leaves, and Susan comes the next day to school, and Mark starts flirting with her. Mark starts flirting with her, and they start dating, and they go through Susan and Mark and Susan go into their junior year, date throughout junior year, and then they go into their senior year, date through the senior year, get up to a couple weeks before prom, and then
Wow, that's
On the day of
doing me
prom.
dirty.
2 weeks before prom.
Wow.
Okay?
I'll go to prom with you.
Thanks, Ryan.
She looks at you funny, starts groaning. Flash of light, chunk of flesh, and then a girl taller than you is there staring at you.
She's pretty.
Very pretty.
Oh, well then, okay.
Okay! Pam has come into existence. It's Pam. No, not her. Why are you staring at her? Pam. Pam. So they continue dating. They date into college. And of course, college, she finds out that Mark is cheating on her. So they break up. And then Pam meets his other guy, Tom. And Tom and Pam are just, they get married. They have 2 kids. They're in their 50s. And then all of a sudden, Pam is in bed. And Bill. Bill. Can you imagine how weird that would be? I mean, all of a sudden, you're Dan and Pam are a married couple, and now Pam has become Bill, and Dan can't handle it. They get a divorce. What is that?
Dan is Tom. Dan is Tom.
Oh, okay.
It doesn't matter.
Okay. Yeah, whatever. I mean, can you imagine what human life would be like if some people like Marie would spontaneously break up and becoming new people? Then there would be people like Allison who would always be Allison till the end of time. Yes?
You can say anything if you go to Kentucky. Just go up there, you'll see if you find
I mean, if you go to San Francisco, it'd be totally normal. That's right. Okay. So, here we go. If you were an atom, this would be your life. Because there are radioactive atoms. Radioactive. Oh. Some atoms are radioactive. Come on, sing along. Okay. All right. So some atoms are radioactive. What that means is that at any moment, they could break up, releasing different types of particles and energy, and actually become something new. Yes?
It's only like some of them or all of them?
No, not all. There are some atoms like you who are not radioactive. you will always stay calcium. If you're calcium, you will always stay calcium. If Marie's calcium, then she could become, let's see, calcium could become scandium. Or calcium can become chloride, argon. That is possible. That is possible. Okay? So, I need to explain two things to you. Number one, how radioactive people like Marie could be dangerous to us. And number two, what are the different bits and pieces that Marie can give off when she undergoes decay? Decay. What does it mean for an atom to be radioactive? That means at any moment it could spontaneously break up, releasing all different types of bits of itself. What are the different types of radioactive particles? And give some equations and how they're produced or captured. Best thing to do is to let Hank Green deal with this.
Radioactive decay occurs when a nucleus has a higher energy level than a potentially more stable version. Typically, this difference in energy is released as what's called ionizing radiation, which you know as radioactivity. It's ionizing because it has enough energy to knock electrons out or add electrons to other atoms, essentially creating ions.
All right, that is ionizing radiation. Ionizing radiation is when a particle or energy comes in, knocks off an electron most of the time, or adds an electron sometimes, and making an atom become an ion. It makes an atom become an ion. Okay? And I hope that by now you realize that that is a significant change. I hope you realize now that sodium is very different from sodium plus 1. Fluorine is very different from fluorine negative 1. So when you ionize an atom, you change its personality. Now, where does the danger come for us? Well, we're made up of atoms. We're made up of molecules. We're made up of proteins and amino acids and all this stuff. So when ionizing radiation ionizes one of those atoms, it could very well change the way the molecule works. Okay, if it's outside in your cell, it could change one molecule into another molecule and mess up the cell. It could even kill the cell. That could be bad. If the ionizing radiation goes into your nucleus, it can change one of your amino acids, thereby changing how the cell works. That could be bad. Though your cell has the ability to fix itself in many different ways. Your cells are amazing. The danger comes if the ionizing radiation were to change some part of the DNA that's in charge of replication. If it alters the way your cell replicates, then that cell could potentially become what? Cancer. Cancer. And therein is the danger with ionizing radiation. Every day you are exposed to ionizing radiation. You have radioactive Maries inside your body. Okay, I mean radioactive nuclei, Marie. I was just trying to go back with the metaphor. It wasn't that funny. All right. Okay. So, I'm sorry, but you're being exposed to ionizing radiation all day long. Most of the time, it doesn't damage you. But since every day you are exposed to it, every day the chances of something bad increases. So by the time you're in your 80s and 90s, most of you will have already encountered or have had to fight off cancer at some point in your life. Folks, most of us will die from ionizing radiation. That's just, it ages us. It kills us. Yes?
Isn't there a form of radiation that treats cancer though?
Yes. We'll talk about that.
Three general types of radioactive
But it still
decay,
hurts.
each named for exactly what is released from the nucleus as it decays. Let's take a look at what may be the most famous radioactive element, uranium. By far the most common naturally occurring form of uranium is the isotope uranium-238. More than 99% of the natural uranium in the world is in this form. U-238 spontaneously decays into thorium-234 in a process that releases something called an alpha particle.
See
This
Marie
is called
becoming
alpha
something
decay,
new?
and the particle that it emits is basically the same as a helium nucleus, 2 protons and 2 neutrons. We even describe it that way when writing it. So right away you can see that the math checks out when it comes to the protons and neutrons. 92 minus 2 is 90, and 238 minus 4 leaves you with 234.
Okay, and here is our first particle. It is called an alpha particle. An alpha particle. It's symbolized by kind of like a fish. It's actually a lowercase a in Greek. Okay? And in essence, it's 2 protons and 2 neutrons. Of all the particles, of all the things that Marie could have released, this is the biggest and most dangerous outside of our bodies. Because it's made up of 2 protons, then we say that it is helium, but it really isn't. So its nuclear symbol is 4,2 helium. Why 4? Because it's 2 protons and 2 neutrons. Why 2? Because it's 2 protons. Okay? So I'm going to teach you how to balance nuclear equations. It is as easy as making sure that these top numbers equal out. Does 238 equal 4 plus 234?
Yes.
Does 92 equal 2 plus 90?
You'll note that we don't write the charges. The helium nucleus obviously has a +2 charge, and the thorium atom would have a negative charge as well. While it's not incorrect to write them, these charges are often omitted to emphasize what's going on in the nucleus. Now, alpha particles have relatively low energy. They're pretty heavy as particles go. So while I try not to make a habit of walking around with a hunk of uranium in my pocket, alpha particles can be stopped by nothing more than a sheet of paper or cloth.
Okay, here's an alpha particle, or an alpha emitter. This is emitting alpha. Ooh, don't worry. Okay, first of all, air is dense enough to block alpha past about 2 centimeters. So this is far enough. But even if it wasn't, even if I had gotten it close to Mark or to Natalie, it's okay. Look, alpha particles can be blocked by the dead skin layer on your skin. Okay, so it's absolutely safe to us outside our bodies. What you do not want to do is to take an alpha emitter like this disc and swallow it. Inside your body, it can do a lot of damage because, like I told you, this molecule is massive. This particle is massive. And as it's making its way through your digestive system, it's up against live tissue, not dead tissue like your skin.
What if you put it on your eye?
Well, yeah, putting it in your eye is not going to be a good thing. You probably would get cataracts from it. That's kind of weird of you to think that way. So along the way, as it makes its way through my digestive system, this alpha emitter is going to be hitting my live cells with giant ionizing particles. Next week.
Ernest Rutherford confirmed that radioactivity involves 3 different types of radiation: alpha, beta, and gamma. Alpha radiation consists of positively charged helium nuclei, that is, 2 protons and 2 neutrons. The radioisotope americium-241, used in smoke detectors, emits alpha particles. The parent nucleus contains 95 protons and 146 neutrons, making a total of 241 nucleons. When an americium atom decays by ejecting an alpha particle, the remaining nucleus has only 93 protons. This is a new element, called Neptunium-237. The decay equation looks like this. Neptunium-237 has 2 less protons, 2 less neutrons, and 4 less nucleons overall. Positively charged alpha particles are affected by magnetic and electric fields, but because they are relatively heavy, they are only weakly bent or deflected. They have low penetrating power and are absorbed in a few centimeters of air or by a sheet of paper.
All right. What's the second type of particle that Marie could release? Yes?
Oh, I was just asking, when it says absorbed by the sheet of paper, what does that mean exactly? What happens?
I'm not exactly sure, other than that particle is somehow incorporated in... I don't know. I was thinking about BSing you, but I wouldn't know how to BS you. Yes?
Just to answer the next question, is it possible that the helium, whatever you call it, +2, it wants electrons, so it gets the paper and attaches?
Probably not. It may just sit there on the surface. Sitting on the surface. How about a beta particle?
Beta radiation consists of high-energy, negatively charged electrons, which are produced in the nucleus when a neutron changes into a proton and an electron. The electron produced is the beta particle. For example, cobalt-60 is a beta emitter used in medical radiotherapy, equipment sterilization, and irradiating foodstuffs. Here is the decay equation. Cobalt-60, with 27 protons and 33 neutrons, a total of 60 nucleons, emits a beta particle, or electron, and the daughter nucleus is nickel-60, with 28 protons and 1 less neutron.
This is confusing, so let me explain it to you. Think of a neutron as being made up of positive stuff and then a little bit of a negative stuff. Okay? It is possible for a neutron to split apart, releasing the negative stuff and just leaving behind the positive stuff. That positive stuff is actually the same as a proton. So when something undergoes beta decay, it releases a tiny little negative particle, which is basically like an electron. It's not an electron, but for all intents and purposes, it is. And then what's left in the nucleus is a proton. Now the reason why the 60 remains the same is, okay, before you had 60 protons and 60 neutrons, and a neutron became a proton. So afterwards you have 60 protons and 60 neutrons. One extra proton, but that doesn't count. We don't care about that. Okay, so that's why the top number doesn't change when it undergoes beta decay. The bottom number changes because what didn't used to be a proton now is a proton. So you have an extra proton because a neutron became a proton, changed its identity.
The second type of radioactive decay is beta decay, which simply emits electrons. It has somewhat higher energy than alpha radiation, but it can still be stopped by a sheet of aluminum foil or even the top layers of your skin. So that thorium-234 that formed when uranium underwent alpha decay, it can continue to decay on its own, and when it does, it undergoes beta decay, releasing an electron and an atom of xenon. Notice that, again, the way we write this is a little different. Even though the thorium emits an electron, we don't use the usual symbol for electron. Instead, we write it in nuclear notation form with the mass number at the top and the atomic number at the bottom. Since it's an electron and not a proton, we put a -1 for the atomic number. That probably seems a little bit weird right now, but next week when we talk about nuclear equations, you will see why it is useful.
Okay, so let me show you a beta emitter. Beta emitters I'm going to have a little more respect for. They can travel about 10 centimeters, so Natalie's still safe. Okay, but it will penetrate into your skin a few millimeters.
Let's do it.
Okay, so it can give you what you would think of as a sunburn. Case in point, I'll never forget a professor I had in college who told me the story of how he absentmindedly placed one of these discs in his pocket. Spent the whole day with a disc in his pocket. When he went home and removed his shirt, his wife looked at him and said, "What is wrong with your chest?" He goes, "I don't know. What is wrong with my chest?" And there was a circular red spot on his skin where the beta particles had been hitting, blasting away at the few millimeters of his skin and basically doing enough damage so that red cells were pouring in, blood was pouring in order to undo the damage. Okay, he got basically a sunburn on his chest thanks to beta. Okay, so now those of you are going to think, "Oh wow, don't want to deal with beta this summer," then you're going to get yourself all burned up to a crisp outside. You know what? You did the same thing. You might as well have played around with this beta disc and rubbed it on your skin all day long because you did the same thing to your skin. That's how dangerous the sun is. Yes?
Will it eventually stop emitting beta and alpha particles?
Yes. We'll talk about this. This has a half-life of 28 years. It'll take a while. Okay, remember that every time Marie or her daughters, and so we're going to call all the people that she became her daughters, Marie and her daughters underwent decay, there was always a light associated with, right? That's gamma.
Gamma radiation is a form of electromagnetic radiation, like radio waves, heat, and visible light. It is found at the highest frequency end of the electromagnetic spectrum, after X-rays. Gamma rays are produced in the nucleus as part of a rearrangement of energy levels after the emission of an alpha or beta particle.
Okay, that's not the gamma.
For example,
Remember, it's the
when a
energy.
uranium-238 nucleus releases an alpha particle and decays to thorium-234, a gamma ray is also produced.
Okay, let me try to explain this to you. Protons, they're positive. And according to the fundamental laws of science, we know that other positives don't like other positives. They will repel each other. And yet, we imagine the nucleus is filled with neutrals and positives, jam-packed together. How? Positives don't want to be with other positives. They believe that there is a strong force that holds it all together. Okay, glues the protons together when what they want to do is spread apart. This force, this very strong force that holds the nucleus together is referred to in science as strong force. Okay, strong force. Some people think of them as bits and pieces of matter that glue things together. They call these things gluons. I'm not kidding. I know, how weird that the force that would hold the protons together would be called strong force or gluons. Okay, basically this. When an atom spits out a piece of itself, it's now slightly smaller. So it doesn't need as much glue. So the gamma radiation that is emitted is that extra stuff that is no longer needed because the atom is a little smaller. Okay? It's leftover strong energy. In AP chemistry, you will actually be able to you can determine the mass of these things to the 10,000th level. And what you'll find is that when you add these two together, it doesn't quite equal this. It's because a teeny tiny little fraction of matter is converted into energy in what we call a gamma ray.
Having no charge, gamma rays are unaffected by electric and magnetic fields. They have low ionizing power compared to alpha and beta particles, but being photons or packets of electromagnetic energy are the most highly penetrating of the nuclear radiations. Gamma rays are mostly, but not completely, absorbed by a lead shield several centimeters thick.
I don't like playing with this one. This one will go about 6 feet, and it will go straight through you. That's the problem. It goes straight through you. It's energy, and you're mostly empty space. So it'll go straight through you. Now, it doesn't have as much damaging power as the beta or as alpha, but whereas beta only goes a few millimeters into your skin, gamma will go very deep into you. So over time, gamma would potentially do more damage if you're playing around with it, because it can go deep inside your body. So you don't play around with gamma either. It certainly cannot convert a normal person into the Incredible Hulk. Yes? That was cobalt-60. That's the same isotope that is used for sterilizing things, like pepper and paprika and medical instruments. Because it'll kill anything that's alive, any germs, any viruses, it'll kill.
The third type of decay is a little different because it only emits energy, not a particle. It's called gamma decay, and it releases electromagnetic radiation similar to visible light or UV radiation, but higher on the energy scale. Because it's just energy, gamma radiation has no mass and contains no protons, neutrons, or electrons, so it's written with 2 zeros. This form of radiation is often released when electrons transition from an unstable, excited state to a more stable state that has a lower energy. That's called the ground state. Depending on how much...
Okay, let's go on. All right. So when atoms decay, what do we call when they what they become? We call it daughter nuclei. So Marie became Matt, I think. That was Marie's daughter nuclei, even though it was Matt. What are daughters nuclei like? Sometimes they are stable, and they'll remain that way for their entire life. Sometimes they are unstable, and they will also decay. A decay series is the entire story, my friends. I told you, I related to you Marie's decay series. It's all the daughter nuclei that Marie became before she finally became something that was now stable for the rest of its life. Okay, here is the decay series for uranium. So this would be Marie, and then Marie would become thorium, protactinium, uranium again, thorium, radium, radon, all the way until you finally get to lead. And lead-206 is stable. Yes?
I understand how, like, you break apart into the 2 pieces, and those are one of the pieces. What? Are the other pieces just kind of disregarded?
No, that's an alpha particle, goes off. A beta particle, an alpha, an alpha, an alpha. Okay? And then what remains is what we're talking about. By the way, if we had 100 Maries, after 4.5 billion years, we would have 50 leads. That's called its half-life. The other 50 would be made up of atoms that are somewhere along this pathway. And that's what we're going to talk about next, half-life. Yes?
So if all these radioactive elements have or decay over time, like, shouldn't all of them run out in millions of years? Or do they somehow go back?
In theory, but we're talking about the Earth is 4.5 billion. In theory, the Earth now has half as much uranium as it used to have when it was first created. Yes?
So does it stay the same? Would you notice a change in volume if you just left it untouched for the whole time period and then looked at it afterwards?
We're actually going to play around. You're going to see the decay, an atom go from being extremely radioactive to not much radioactive at all next week. I don't think you're going to see a significant change in its mass. Not one that we can measure. In theory, yes, you should see a change. I'm not sure we have instruments sensitive enough to be able to detect that change. Because we're not talking about that much mass being lost. Okay, so can we now balance nuclear reactions? Let's see. We shall begin with Natalie. Natalie, 11.6. Before I forget, let me kind of take you through all the different types of particles once again that you will encounter. The little fish is alpha, and its nuclear symbol is 4,2 helium. 4,2 helium. the B with the little tail on it is what the British would call beta, what we call beta. Kind of getting used to the way they call it, beta. I think it's kind of cool, beta. And that's 0, -1, E. It is possible, remember how a neutron became a proton and a beta particle? It is possible for the reverse to happen, for a proton to become a neutron and a positive beta. That's called a positron. A positron. It is, in essence, a tiny little particle that is positive, that's about the size of an electron, but it's positive. It's actually thought of as being antimatter. So those of you who are into Star Trek, this is an example of antimatter. Okay? Then the last one is symbolized with an N, and it's basically a neutron. And it's going to have a mass number of 1 because mass numbers are protons and neutrons together. It's going to have an atomic number of 0 because a neutron is not a proton, and it's going to have an N. Okay? Got it?
Would that be considered gamma?
No, no, gamma is pure energy, so gamma does not play a part in these nuclear reactions.
Okay, so on our homework, which one was the third symbol? That's not one of the options.
There's 1 0 and an N, which is that.
Neutron. Okay, forget about the options. There's more options than that.
Okay.
Add neutrons and positrons to your options.
Okay.
All right, here we go. Natalie, 11,6 carbon emits a positron. What is the symbol for a positron? No, that's its letter symbol. I'm talking about its nuclear symbol.
Oh, 0, +1.
Okay, that's a 1. Positive 1. All right, here we go. You may need a calculator. You're definitely going to need a periodic table for this. Oh, I forgot to tell you guys that whenever we're doing chemistry, please keep out a calculator and a periodic table.
Yeah, maybe next time you won't drop the ball on the...
I know, I'm sorry. I keep forgetting to tell you this. All right, Nat. You ready?
I think so.
Imagine this arrow is equal sign. So 11 equals 0 plus what?
+1. Wait, no, +11?
Yes, 11. Use a calculator if you need to have it. 11 plus 0 is 11. Yay! Does that number help identify what it is? No. Because you can have any number of isotopes with a mass number of 11. Okay? That is absolutely useless to us. Let's try it again. 6 equals 1 plus what?
5.
Very good. Now can we identify it?
Yeah.
Who is number 5?
Boron.
Natalie.
Good job, Natalie.
Boron.
Hey, that's my girlfriend.
And that is a balanced nuclear equation.
Oh, that's it?
That's it. Marieli.
No, I didn't want to do the next one.
214. Oh, no. I heard the way you said that. That was like, that's easy. That's it. 21483 is a beta particle emitter. So what is the symbol for a beta particle?
0, -1, E.
All right? Use your calculator if you need to. What plus 0 is 214? Wow. She's so smart. What minus 1 is 83?
94.
Might want to use a calculator.
Wait, what?
Not 94. What plus minus 1 is 83?
I thought it was 9.
83.
84. I am good at math.
Who is number 84, Marieli?
Oh, okay. Po something.
Polonium.
Yeah, that.
Police. All right, 237, 93 Morgan Neptunian yields an alpha particle.
Okay.
What is the symbol for an alpha particle?
It's the little
Not a Greek symbol, the nuclear symbol.
the 4 over 2
All right, you ready? What plus 4 is 237? What plus 2 is 93? Who is 91? Protactinium. All right, let's continue. Now it's fill in the blank. Ryan, 195 plus what is 195? 79 plus what is 78?
Oh, now was the dummy.
What? So 79 plus 1 is 78? And who has a 0, negative 1?
Is that the, I forgot what it's called, but it's the photon.
Look on your chart that I'm sure you wrote down.
Positron, that's
No, that's 0, positive 1. Somebody help the man. Beta.
Good job, Ryan. Good job.
Okay. Don't lie to your own voice.
Esther. 38 equals 38 plus what? 19 equals 18 plus what? What is that? Positron. Positron. Grant. 241 plus 4 equals 2 times 1 plus what? Let's try that again. 241 plus 4 is what? 2 plus what gives you 245? 95 plus 2 is? 20 is? What plus 0 is 97? So who's number 97? Home of the Whopper, man.
Burger King.
No, berkelium. Jeez.
I was like, Burger King?
Allison. 214 plus 2 fours. What's 2 4? What's 2 fours? 8. So 214 plus 8 is 222 plus 2 zeros is 222. 84 and 2 twos is, so 84 and 4. Try again. 84 and 4. 84 and 2 minus 1s. So 88 and minus 2 is, who's number 86?